In this chapter, we're going to study gradient descent optimization method for deep learning or neural net in general. The gradient descent method is the training method used in deep learning. So in this chapter, we're going to study some method which can improve the performance of gradient descent. So more specifically, you're going to cover the following, including loss functions, activation functions, and some variants of gradient method, and also some other method about learning rate and momentum stuff, and weight initialization, and some other tips to improve gradient descent. Gradient descent is the basic learning method in deep learning and neural net. And this gradient descent is also used in many other machine learning algorithms as well. So there has been a lot of efforts to improve this gradient descent method. Okay. So people improve this basic gradient descent method in many different directions. So if you take a look at this basic form of gradient descent, so this part is the basic formula of gradient descent. Let's say W is the parameter of your method. In deep learning case, this should be the weight in network. Right, so new value of W is the old value of W minus learning rate times the derivative of error function F. So that's the basic formula of gradient descent. So this is basic form, and people try to improve this basic form in many different directions. Okay, so the first direction is some people try to improve this learning rate part. Learning rate is constant. Okay, so you're going to improve it. Okay, you're going to replace this learning rate constant by some functions. Okay, that's the first direction. So that's here. Okay, so we try to improve learning rate part, and many work is done, including AdaGrad, RMSProp, AdaDelta, Adam, etc. Okay, so we're going to talk about it. So this is the first direction of improving gradient descent. Second direction is, some people try to improve this error function. Okay, so that includes, we try to improve error function, and that include MSE, cross entropy, KL divergence, and many more. Okay. And the third direction is within the error function, we do have what is called activation function. Okay, it used to be called output function, but now it is called activation function. So whatever you call it, we do have activation function. Okay, in older days we use sigmoid function, but now we have many more options for activation functions. Okay, so that's the third direction for improving gradient descent here. Okay, it includes ReLU, Leaky ReLU, etc. Okay, and finally, the fourth direction is we're gonna add some other term here. Okay, to improve the gradient descent, and this term may be momentum. Okay, of the function, or it may be a regularization, maybe L1 regularization or L2 regularization, etc. Okay, so you can add some additional term here. Okay, that's the fourth direction to improve the gradient descent. So in this chapter, we're gonna cover all this method to improve the gradient descent method. Let's begin with loss function first. Loss function is also known as error function. So loss function is basically a function which defines the size of error. So you define loss function first, when you apply gradient descent. And then your algorithm is basically trying to minimize loss function. That means your algorithm is trying to minimize error of algorithm, right? So that's definition of loss functions. There are many loss functions we can choose from. Okay, so we're going to talk about it here in this section. For notation purpose, P sub I is the predicted value of your method, and Y sub I is the true value of data. So let's begin with the 0, 1 loss, which is defined like this. And this 1 is just, it is just identity function. That means if Pi and Yi's are equal, then this returns 0, okay? And these two values are different, then this returns 1. So this returns either 1 or 0. So if these two values are equal, this returns 0, and if these two values are different, this returns 1. Okay, that's 0, 1 loss. So you do all the summation and divide it by, and it's basically you calculate average. Okay, so that's 0, 1 loss. But this one is not, it's very rarely used. Not many people use this, because this is not differentiable. Okay, we are using gradient descent. In gradient descent, we take derivative of error function, and this one is actually not differentiable. Okay, and that's one reason of not using this 0, 1 loss. Okay. By the way, sometimes we use this part only. Okay, without this n over 1 over n, you use this part only, and this is now is called L1 regularization term. We have learned it in our regularization part. Okay, so if without this part here, 1 over n, this is sometimes used as a L1 regularization term. The second loss function is hinge loss function. So the formula of hinge loss function is maximum between 0 and 1 minus pi yi. Again, pi is our prediction, and yi is a true or target value. Hinge loss is for binary classification with target value -1 and 1. So if you have a multiple non-binary classification, you cannot use hinge loss. And also, if your classification class value is like 0 or 1, okay, binary, but 0 and 1, but you have to change the 0 to -1, okay? So the class value should be 1 and -1, okay? And the basic idea of a hinge loss is the following. The performance of correct prediction should be greater than the score or performance of incorrect predictions by some margin, okay? So yeah, the score of a correct prediction should be greater than the incorrect predictions, right? But it's not enough. Its score of correct prediction should be greater than the incorrect prediction by some margin, okay? So what I mean by that is the following, okay? So suppose when this PI, YI have opposite signs, so PI, YI have opposite sign means our prediction is wrong, right? So in that case, our prediction is wrong. Definitely we have error. Okay, so in that case, the hinge loss actually increases linearly with Pi. If you look at this picture here, this x-axis is Pi times Yi, and this y-axis is the value of hinge loss. So if pi, yi have opposite signs, okay, then this pi times yi becomes negative, right? Negative. So it is pi times yi is negative. You can see clearly, you can see the hinge loss increases linearly with the value of pi, okay? Yi is fixed, so with the hinge loss increases linearly with the value of pi, okay? You can see that here, okay? So this case is this one line here. Then if the pi and yi have the same sign, that means same sign means the prediction is correct, right? Again, the class value is 1 or minus 1. So if both pi and yi have the same sign, that means our prediction is correct, okay? But be more specifically, if the absolute value of pi, our prediction value pi, the absolute value is greater than or equal to 1, then our loss is 0. This is the case here, okay? So PIYI has the same sign. That means our prediction is correct. But also at the same time, the absolute value of PI, our prediction should be greater than 1. In that case, our loss is 0, okay? You can see here. Then in this case here is if even though our prediction is correct, okay, PIYI have the same sign, okay, our prediction is correct, but if the absolute value of pi is less than 1, okay, then still this hinge loss generate error. It's right here, 0, between 0 and 1 here, okay? So even though our prediction is correct, PIYI is positive, means they have the same sign. That means our prediction is correct, okay? So even though our prediction is correct, the hinge loss still generate error like this, right? So this is the error of hinge loss when our prediction is correct, okay? That's the main property of hinge loss, okay? So, in this case, for example, let's say our correct value, yi is 1, okay? And our prediction, so correct value is 1, and our prediction is like, let's say 2, okay? Then our prediction is the absolute value is greater than 1, so our loss is 0, okay? This is this case here, okay? But if the target value is 1 and our prediction is like, let's say 0.5, then absolute value is less than 1, right? Then our hinge loss generate error like this, okay? It still generate error, okay? That's the idea. So if the prediction is 0.5, this prediction is correct, but the idea of hinge loss is this is not good enough, okay? The correct value is 1, but our prediction is 0.5. This prediction is correct, but not good enough. So the idea of hinge loss is the score of correct prediction, the performance of correct prediction should be is better than the incorrect prediction by some margin, okay? In this case, 1, okay? So here, if the prediction is 0.5, simply say this prediction is correct, but not good enough, okay? That's the basic idea of hinge loss. So that was the formula, and that's the basic idea of hinge loss. And this hinge loss is mainly used in a maximum margin classification. The typical example is SPM. So SPM uses this hinge loss. As you can see here in this formula and this explanation here, this hinge loss gives a high penalty for wrong answers, okay? And also this, if you look at the formula here, this is not differentiable, right? Because we have max here, so it's not differentiable. But the good news is this is convex function. As you can see here, this shape is convex form, okay? And because this is not differentiable, sometimes we use something called the squared hinge loss. That's basically a square form of this, and it's also available. Okay. So this is hinge loss. The next loss function is mean absolute error and mean squared error. In short, we call it MAE and MSE. These two are very similar actually. If you look at the formula, mean squared error is actually the square form of MAE. But there are a lot of similarities and also some differences between these two. So let's go over MAE first. Okay, MAE is basically the absolute value between this prediction and target value. But this one here, one of the problem of this one is, again, this is not differentiable. Okay, this is absolute value. Okay, we cannot differentiate absolute value. So because of that, when you use MAE, we use some approximation. You simply assume its derivative is 1 or minus 1. Or you can use another approximation function which is differentiable. Okay, so that's kind of getting around this problem. Second thing here is it's more robust to outlier is compared to this one. Okay, so if you compare these two, this MA is more robust to outlier than this one. So what I mean by that is outlier is like this. Let's say most of data is in a certain area like here. Okay, so let's say most of data is somewhere here around here. Okay, most of data is here. Okay. And we have one particular data which is way back here, okay? And this data is called outlier, okay? And in many cases, this outlier is actually error or noise, okay? So if you use MAE and you calculate this value, the error, for this particular outlier, okay, and also you can calculate this size of error using MSE here for this particular outlier, okay. Then if you compare these two, okay, this value is much higher than this for this particular outlier, okay. So I said this outlier is in most cases error or noise. The data itself is wrong, okay? So if you calculate error like this, for this particular data, the error itself is error. It's very very strange expression, but it's wrong error. Its error is not correct, okay? So it gives this error actually. The error of this outlier actually gives negative influence to the loss function, okay? So in that sense, this is the size of error for this particular outlier, and this is size of error for this particular outlier. If you compare these two, this value is much higher because this is squared, okay? So in that sense, we say MAE is more robust, more stronger, okay, than more robust to outlier than MSE, okay. So if you assume there is possibility that there are lot of liars in the data, maybe you can choose MAE instead of MSE because MAE is more robust to outlier, okay. Okay, move on. There are some similarities as well. Both MAE and MSE, you can use both either in classification or regression. You can use this for classification and also you use this functions to regressions as well. Okay. Right. Let's move on to MSE. Okay. This is the formula of MSE. So the only difference between these two is we calculate square of this one. Okay. Actually, this is very popular loss function. Okay, and sometimes we use log form of this. So instead of this, we use log pi minus log yi. The reason is we put log when these pi and yi values are big. Okay, so in case there are some cases where these pi yi values are very big. Okay, in that case, yeah, think about it. If these values are very big, its square is huge, right? So it's no good. So if this PIY values are very big, we put log there and kind of reduce the size of value, right? So sometimes if these values are too big, maybe you can put log there, okay? And if you compare these two, usually you can say this MSE is better than MAE. This is very popular loss function. But if you use MSE with sigmoid function, actually it saturates, okay? And the reason is if you use a sigmoid, its value is between 0 and 1, okay? That means these values are very small, between 0 and 1, and you scale them, okay? So these values are less than 1, and you scale them, okay? Then this value is even smaller, okay? So it makes the algorithm training very slow. So it is not a good idea to use MSE with sigmoid expansion function. It makes the training slow or even saturates. Okay. Finally, in MSE, if you remove this part, okay, and use this one only, and I think this is familiar to you, and this is the L2 regularization form, okay. So if you remove this part, you can use this part as the regularization term of the gradient descent. Okay. The next loss function is cross entropy. Actually, the cross entropy is one of the most popular loss function we use these days. So this is the formula of cross entropy. Okay, so y is the target value, p is the prediction. Okay, so minus y times log pi. We have binary cross entropy and multi-class cross entropy. So in binary, the class value is binary, and the multi-class, the class value is more than 2. Okay. Let's move on. And if you look at this formula of cross entropy, basically what it means here is, so cross entropy is, do you remember when the probability, so pi is probability of a certain event, okay? Do you remember what this log pi means? Log pi means the information of pi. Pi is probability, and if you put log in front of probability, it is information of probability. Okay, that's the amount of information that this probability pi contains. Okay, that's the definition of information of probability pi. So this one here is actually the average with respect to y. So basically cross entropy is the average value of information of p, average value of information of p with respect to y. We calculate average value of information p with respect to y value. Okay, that's definition of cross entropy. The characteristic of cross entropy is it gives a lot of penalty when the prediction is very competent or very wrong. So for example, if you look at this picture here, let's say the true value is 1. Okay, true value is 1. And this is your prediction. So if your prediction is very close to 1, it's error is very small, okay? It's very close to 0. But if the prediction is very low, like 0, okay, the true value is 1, okay, this is wrong, very wrong, right? And then its error actually skyrockets, right? So error is very wrong. It has very high value of loss, okay? That's the characteristic of cross entropy. So it gives a lot of penalty when the prediction is very wrong, okay? So we use cross entropy in many classification problems, okay? Again, as I said, this cross entropy is one of the most popular loss function in the classification problem. Especially this is good when you classify for small number of class values, okay? And unlike the MSE, in MSE, I said when you use MSE, you better not to use sigmoid function along with MSE because it makes the training very slow or even saturate, okay? But in cross entropy, it actually doesn't matter, okay? This cross entropy gives very nice performance regardless of the activation function you use. Okay, that's another advantage. And generally, this is faster than MSE. So that's a cross entropy. And then move on. It's Kullback labeler measure. That's another loss function we use. It's short, we call it KL measure or KL divergence. And this is definition of KL divergence. If you rearrange it, this is entropy, and this is entropy. So it is joint entropy between P and Y. This is entropy of Y. So this one here is same as this, right? So KL divergence is actually cross entropy minus entropy of Y. Okay. So the original definition of KL divergence is, suppose we have two probability distribution. We have two probability distribution. Okay, don't worry about this loss function, classification, whatever. So in general, we have two probability distribution. Okay, and you wanna calculate, the difference between these two probability distributions. Okay. How different are they? You want to know, okay? Then this KL divergence is very nice measure to calculate the difference between two probability distributions, okay? This is widely known as a measure of calculating the difference between two probability distributions, okay? Okay, so if you look at this formula carefully, so KL divergence is cross entropy minus entropy of Y. So Y is the target value. So when Y value is fixed, so you have data and their target value is fixed. It doesn't change, okay? Then actually this is fixed, right? Target value is fixed. Actually, in most cases, target values are fixed. Okay, we don't change target value, so it's already fixed. Then, in that case, if you use a cross entropy or KL divergence, actually it's the same because this is fixed, right? And this is same as this is cross entropy and minus. If target value is fixed, this is constant, right? So in that case. So if target value is fixed, which is true in most cases, if you use KL divergence or cross entropy, the problem is same. The loss function is same. Okay? But for some reason, if the target value changes, okay, then you train algorithm, then definitely these two are different. Okay, but that's very, very rare. Okay? Now let's talk about activation functions. the first activation function we're going to talk about is sigmoid function. We have seen this sigmoid function before in neural net, so it's kind of review. So sigmoid function, this is shape of sigmoid functions, and it ranges between 0 and 1. So it takes input x, and actually it squashes. Okay, it squashes its output in between 0 and 1. It looks like this. Okay, that's actually the shape of sigmoid function. So you take input and squashes output between 0 and 1. Okay. So in sigmoid function, when the activation value is near 0 or 1, so when the output is near 0 and 1, around here, okay. So we use gradient descent. That means we use the derivative of this activation function, right? Then when the value is near 0 or 1 around here, its derivative is actually very close to 0, okay? Its derivative is close to 0, okay? So because this derivative is 0 around here and here, actually we have a problem called the vanishing gradient problem, okay? We talked about vanishing gradient problem in the introduction of deep learning. Okay, that's one of the biggest problems of neural net with many layers. Okay, because of vanishing gradient problems, actually it doesn't make sense to add many hidden layers in traditional backpropagation neural net, right? So one of the reasons is because we use sigmoid. When you use sigmoid activation function, okay, in many cases the output is very close to 1 or 0, okay? And the thing is, if the output is near this 1 or 0, its gradient is almost 0, okay? That causes vanishing gradient, okay? So you multiply this gradient many times, and each gradient is almost 0, okay? So you multiplied many times, then at the end, the answer is pretty much 0, okay? So nothing happens. And that's vanishing gradient problem, okay? So that's why, this sigmoid function is, these days we don't use sigmoid function, we don't use it anymore actually, especially in deep learning. The main reason is if you use sigmoid function, it causes vanishing gradient problem, okay? Second thing here is if when you initialize the weights, if the initial weights are too large, that means we are near this value, okay? So this thing happens. If the initial weights are too big, that means the output is very high probability that output is near here, okay? So the neuron becomes saturated, and this thing happens. We have this thing happen, okay? And this is slow in convergence, okay, because in many cases gradient is very small. That makes this training very slow, okay, slow in convergence. And another problem of sigmoid is, as you can see, this output is always positive, okay? It's not zero center, it's always positive. So suppose the every data every data is positive, then every gradient is positive as well. So every data is actually positive. So if you use sigmoid, actually this training moves on in one direction only, okay? It doesn't go in zigzag form. It just follow in one certain direction, okay? Always positive or always negative, okay? So that's another problem. Another problem of sigmoid is it's computationally very expensive. If you can see here, you have to calculate this exponential here. It is very expensive to compute. Okay, so sigmoid is very slow actually. You use sigmoid, your training is very slow because you have to, every time you have to compute this exponential value. Okay. Finally, you can use sigmoid in output layer of classification, okay, and because it ranges between 0 and 1, okay. So even though we do not use sigmoid, often these days, but sometimes you use sigmoid as in output layer of classification because it returns value between 0 and 1, okay. So in many cases we still use sigmoid especially in output layer of classification. The second activation function is hypotangent, and this is the shape of hypotangent, and this one is very similar to sigmoid function. So the only difference here is actually in hypotangent you shift the graph downward a little bit, and it now ranges between 1 and -1, okay. That's the only difference between hypotangent and sigmoid. So in hypotangent, it read input and the output is squashed between -1 and 1. And this is the formula of hypotangent. And actually, as you can see here, the hypotangent is actually this 2 times sigmoid function -1, okay. So that way you can convert sigmoid to hypotangent, okay. It's very similar. So as I said, it's very similar to sigmoid function, and because it ranges between its range is limited between minus and 1. In sigmoid case, the output is ranged between 0 and 1. Because of that, we can use sigmoid as in output layer, okay. For the same reason, hypotangent output is limited between minus and 1. And because of that reason, you can use hypotangent in output layer of classification, okay. So that's the hypotangent, and because these two hypotangent and sigmoid are very similar, it has very similar characteristic with the sigmoid function. So like a sigmoid function, this hypotangent can saturate. That means the gradient is very small. It causes vanish gradient problem, okay. And there's one difference here is, as you can see here, in sigmoid is not zero-centered. Everything is positive. Okay, that was one problem. But in hypotangent, the output ranges between minus and 1. Okay, so we have plus and minus. So that's the advantage of hypotangent over sigmoid. It is zero-centered. Okay. So when you use gradient descent, it can move it doesn't move in one direction only, okay. It can move in any direction, okay. This plus minus. So in general, this hypotangent is preferred to sigmoid function, okay. And also this, when you calculate gradient of hypotangent, its gradient value is actually much stronger. This gradient here is much steeper than sigmoid in general. So if you use hypotangent, gradient is much stronger. Okay, that means your training is much faster because gradient value is higher in hypotangent than in sigmoid function. The next activation function is ReLU, R-E-L-U. It stands for rectified linear unit. Actually, this ReLU is one of the most popular activation function in deep learning. This is the shape of ReLU. As you can see here, this ReLU function is very simple. Okay, so if the x is negative, it returns 0, and this x is positive, it returns x line, okay, linear line. So this function is super simple. So because this function is very simple, okay, actually it is this activation function is very fast when you train deep learning. Some people, it is known that some people say this Lulu function is actually 6 times faster than the other activation function like sigmoid or hypotangent. Okay, it makes sense because when you compute this activation function, the Lulu is very simple here. But when you compute sigmoid, you have to actually compute the exponential value, right? So which is very time consuming, so it makes sense. So Lulu is very fast. And secondly, it's, as I said, this Lulu is the most popular activation function, especially in deep learning with many hidden layers, and very easy to implement. As you can see, this function is super simple. It's very easy to implement. The other thing here is you have to keep this in mind, and you can use Lulu function in hidden layer. Because deep learning has many hidden layers, you can use Lulu, in hidden layer. That's fine, but do not use Lulu in output layer, okay? Because this Lulu function returns value between 0 and infinity, right? It can be any number between 0 and infinity. Okay, it can be big number, right? So because of that, it is not a good choice to use Lulu in output layer, okay? So instead of using Lulu in output layer, you can use sigmoid or hypotangent for binary classification, or you can use softmax function for multi-class classification. So your work on classification problem, okay? Then you can use Lulu in the hidden layer. That's fine. But in output layer, do not use Lulu. You use your problem is binary classification. You can use sigmoid or hypotangent. If your classification is multi-class, you can use softmax as an output layer. Okay. Or if you happen to work on a regression problem, you can use linear function as the activation function. Okay. So anyway, the thing is, you can use Lulu in hidden layer, but do not use in output layer. If you work on classification problem, in output layer, you can use sigmoid or tangent for binary classification, or you can use softmax if your work is multi-class classification. Okay. This is computationally efficient. This is clear. This function is super simple, so computationally very efficient. And but some of the problems of Lulu is, if you can see here, if x is negative, this returns 0. So output is 0. So actually what happened is if you use Lulu in many hidden layers, many of the hidden nodes are actually dead. That means its output is 0. It does nothing. Okay. That's what actually happens. Okay. So many Lulu units simply die. Die means output is 0. Okay. And it never recovers. It simply die, and from that moment on, it never reactivate. Okay, so that's the problem of Lulu. That's what happens. And the other problem of Lulu is sometimes this output may return very high value of output, right? So in that case, actually this Lulu blows up the activation. It returns very high value of result output function. Okay. So that's another problem of Lulu. The next activation function is called leaky Lulu. It is similar to Lulu, but there is slight difference here. If you look at this picture here, this is shape of leaky Lulu. In traditional Lulu, this is shape of Lulu, right? And the x is negative, it returns 0. Okay. And because of this, I said many of the Lulu unit actually die, okay, and nothing happens after that, okay. So that is the problem. So to solve that problems, people come up with a new activation function called leaky Lulu. So this is shape of leaky Lulu, okay. So in the negative part here, instead of 0, it returns a small value of slope here, okay, like this, okay. So if x is negative, its gradient is very small, not 0, okay. So that way, gradient is not 0 now, okay. So that way you try to solve the problem of dying, okay, dying neuron, right? So that's liquid glue, but it is unclear whether this liquid glue is better than the glue, traditional glue. Okay. So we don't have a very conclusive result saying liquid glue is better than the glue or the other way around. This is unclear. Okay. So we do have this liquid glue to solve the problem of dying neuron, but it is unclear whether this actually is better than the glue. Okay. So anyway, if you run your algorithm and actually you have to see, during the training, you have to see the proportion of dead neurons in your algorithm, okay? And if there are many dead neurons during training, maybe it is a good idea to change the glue to liquid glue for your algorithm, okay? There are some variants of liquid glue, okay? We have another one called P glue. Actually, P glue is, in liquid glue, you can decide the value of slope here, okay, by giving alpha. This is slope of this line here, negative line here. That's P glue, okay. So slope is another parameter, okay. That's basically determines the slope of negative line here. Okay? That's P glue. And another one is called E glue exponential linear unit. So in negative part, instead of line, you use a little curve here that looks like this. This is the shape of curve in this part. Okay. So negative part is a curve instead of line, and it is called ELU, okay, exponential linear unit, okay. So again, which one is better than the other? It's a little unclear. You need more study about this topic, okay. The next activation function is called the max out. This is the shape of max out, and this is the formula. So actually what happened here is you draw two line, whatever, okay, and for a certain value of x, you choose bigger, large value between these two, okay. So in this case, this is bigger than this, right? You choose this one here, and this part, this is bigger, so you choose this part, okay. So that's max out. And we have seen glue and liquid glue. As you can see here, glue and liquid glue are special case of this max out form, okay. So it enjoyed all the benefits of the glue unit. That means this computation is relatively simple compared to sigmoid or others, okay. And because it is simple, and it doesn't have the drawback of dying the glue, okay, because there is, in glue, the negative part, it returns 0, right? But max out, everything is positive here, so it doesn't have problem of dying neuron, okay. But problem of this is, unlike glue, its number of parameter is double, okay, so it needs more training time to use, okay. And finally, because this is very new activation function, so whether this actually is better than Lulu or other activation function, to see that we need more study, okay, more study to see whether this actually is better than the other, okay, right. So right now we have this max out, but whether this is absolutely better than the other is a little unclear. Softmax is another activation function, and this one here shows the functionality of softmax. So this part here is the output of network deep learning. So it had three outputs, 0.8, 1.2, 3.1. So softmax, what softmax does is it read this vector of output and change this to a probability distribution. Okay, so this becomes this, and this is now probability distribution. So probability distribution means summation of this is 1. Okay. So this is the formula of softmax. So Z, actually Zi is represent the output value here. Okay, so each output value Gi is transformed like this. Okay, so it becomes probability distribution. You can see here the summation of this is this, right? So it ranges between 0 and 1. Okay, and this whole vector is probability distribution now. Okay. You can use softmax in last layer, output layer only. You don't use this softmax in hidden layer, okay? And use softmax in multi-class classification problem, okay? And when you use softmax, the number of input and number of output should be same. It is very clear, right? It simply changes this output into probability distribution. So this number of data here, number of data should be same. Okay. So actually, what softmax does is it squashes entire data into ranges between 0 and 1, and summation is 1. Okay, that's what this softmax does. And each value now ranges between 0 and 1 because it's a probability, and the summation should be 1 because it is probability distribution. Okay. Because it changes output into probability distribution, it mimics the one-hot encoding. One-hot encoding is we have a number of bits, binary bits, and only one of them is true. Okay, that's one-hot encoding. That's one way of representing word, language word. Okay, so it's similarity there. Okay. And again, as I said, you only use softmax in output layer. Okay, don't use it here in hidden layer. And finally, if your problem is multi-level classification means you have data, okay, and its target value is more than 1. Okay, it is like you have image. This image, belongs to it belongs to a person. It belongs to a certain I don't know, maybe a nature. Maybe this person is playing golf in a mountain area. Then you can classify this as person. Also classify this as mountain, etc. Right? So when a certain data belongs to more than one class value, it's called multi-label classification. So in that case, do not use softmax, okay? Instead, you use sigmoid function, okay? So that's one thing you have to remember when you use softmax. The last activation function we're going to talk about is switch activation function. This function is very new. It's proposed, I think, 2017 by Google. This one here shows the shape of switch function, and this one is the loop function. So the two are very similar. And switch in negative part is not 0. It's a little curve here. Okay, so it doesn't have the problem of dying neuron. Okay, but the shape is very, very similar to the loop. Okay, and this is the formula of switch. Actually, it is the x is multiplied by sigmoid x. Okay, the formula is very simple, and this is shape of switch. And it is again proposed by Google, and they say it performs better than ReLU, okay, with the same similar level of computational efficiency. So they say this switch is better than ReLU, okay. So this is because this is very new. We will see whether this switch is actually better than Lulu or not. Okay, so we will see. Okay. The next topic is variant of gradient descent. The issue here is, so in gradient descent, you define error function and you take the derivative of error function and update your parameter, right? So question is, how often do you update your parameters? Do you update your parameter for every data, or do you update your parameter after reading entire data, etc.? Okay, so how often do you update your parameter? That is the question of this subject. Okay, so we're going to see three variants of gradient descent method. Okay, the first one is called batch gradient descent. So we use gradient descent. In batch gradient descent, what we do is you read entire data, okay, entire data, and then you calculate the derivative by using entire data, okay, and then you update parameter, okay. That's a batch gradient descent, okay. But as you can imagine, this is very slow. Okay, yeah, suppose, imagine you have lots of data, then you read entire data and then you update once. You know, it is very slow, okay, and almost intractable, okay. So anyway, that's batch gradient descent. Second case is called stochastic gradient descent. In short, we say SGD. So unlike batch gradient descent, in stochastic gradient descent, you read one data, okay, and for each data, we read one data and update parameter, okay. So this is much faster, okay, and you can do this even online, okay, so very, very fast. But the problem is, if you compare these two, batch gradient and stochastic gradient, the gradient in batch gradient value in batch gradient descent is very actually stable. Its value has very low variance, okay. It doesn't fluctuate. Its value is quite stable, okay. But if you use stochastic gradient descent, the gradient value, it actually fluctuate a lot. Sometimes it's very high, sometimes it's very low, okay. So it has very high variance. That is the problem, okay. So each method has its own pros and cons, okay. That's batch and stochastic gradient descent. The third method is called mini batch gradient descent. It is somewhere in the middle between batch gradient descent and the stochastic gradient descent. Okay, so if you look at this picture here, in batch gradient descent, you read entire data and update. Okay, and stochastic gradient, you read one data and update. Okay, so these are two extreme cases. So we meet somewhere in the middle. So mini batch gradient descent basically means you read a small batch of data, okay, like 50 or 100 data, whatever, okay. You read a batch of data, okay, and then you update here, okay. Then next you read another batch, it's called mini batch, and then update here. Okay, so that's called mini batch gradient. Okay, so it's middle, somewhere in the middle, compromise between these two batch gradient and stochastic gradient. So actually, this mini batch gradient is the most popular method we use in training deep learning. Okay, so it takes the best of both methods, batch gradient, stochastic gradient. Okay, so update for every mini batch. So you can reduce the variance of parameter updates in the problem of stochastic gradient was its variance is very high. Sometimes value is very high, sometimes very low. Okay, it's high variance. So somehow this mini batch reduces the variance. Okay. So the common mini batch size is range between 50 and 256. Okay, this is common mini batch size, but you can change if you want. Okay, so it can vary for different applications. So this picture shows the update process of gradient descent here. Okay, so gradient descent is like this. Okay, now in batch gradient descent, the value is very stable. It doesn't fluctuate. Okay, it's low variance. So it's very moved like this, very steady. Okay, very smooth. But on the other hand, if you use stochastic gradient descent, its variance is very high. It fluctuates. It moves like this. Okay. It means very high variance. Okay. So in many cases, eventually you're going to reach to this point, but no guarantee actually. Okay. Next method is about improving momentum, and it is called NAG. NAG stands for Nesterov accelerated gradient. So this one is the formula of traditional momentum. So this is a gradient. This is a learning rate. So in addition to the gradient value, we add this V is the gradient of previous step, and this gamma is constant called momentum constant. Okay, so what we do here is we follow the direction of a previous step a little bit, okay, and also we follow the current gradient. Okay, so by adding together we have a new direction. So this picture shows the momentum update. Okay, so this is the momentum step. So this is represented here as this arrow here, and this one here is actually this arrow. Okay, so at this point you calculate the momentum and you calculate gradient at this point here. Okay, and then you add this, so that means this is the final direction you want to follow. Okay, this is the traditional momentum. The idea of NAG is as follows. Okay, suppose so you in here you calculate gradient in this point. Okay, suppose the error surface in at this point, and the error surface at this point is quite different. Okay, for example, here it's downslope, it's upslope, whatever. Okay, its error surface is very much different. Okay, then calculating gradient, and at this point actually doesn't make sense. Okay, so instead of calculating gradient here, you follow this momentum first, and then you calculate the gradient at this point. Okay, which makes more sense, because if the error surface of this place and this place are quite different, okay, then calculating gradient here actually doesn't make sense. Okay, so that's the basic idea of NAG. So if the error surface of this point and this point are quite similar, no difference. Actually, this NAG and doesn't make much difference than the traditional momentum. But if these surfaces are quite different, actually this NAG shows better performance than traditional momentum method. Okay. So in NAG, the update rule is changed as follows. The only difference here is instead of calculating gradient at theta, you calculate the gradient at theta minus gamma vt minus 1. This is the estimate of new direction, new point here. Okay, you follow momentum first, and this is the point where you end up. Okay, so that is NAG, and it is known that NAG generally is better than traditional momentum method. Next topic is about method for improving learning rate in gradient descent. So this is the basic form of a gradient descent. Okay, and this is the learning rate, constant. So we assumed it is constant so far. So this learning rate is same to every parameter, to every iteration. This learning rate is constant. Okay, so you're gonna change it in this method. So the first method is called AdaGrad. So the basic idea is we maintain a different learning rate for every parameter. Okay, so we maintain a per parameter learning rate. Okay, so in traditional gradient descent, we have the same learning rate to every parameter, but AdaGrad, each parameter has different learning rate. Okay, and the idea is for some parameters we update very frequently. Okay, we have a lot of update for that parameter. In that case, we decrease the learning rate. Okay, on the other hand, for some other parameters we rarely update it. Okay, so these are parameters with infrequent update. Okay, in that case, maybe we can increase the learning rate for those parameters. Okay, so that is the basic idea of AdaGrad. So this method is well suited for dealing with sparse data. So sparse data means this data, for this data we update very rarely. Okay, infrequently. So this is the formula for AdaGrad. So if you compare this with the traditional gradient descent, this learning rate is replaced by this. Okay, so actually the only difference here is this eta learning rate is divided by this one here, right? This epsilon is a very small constant. Okay, don't worry about this. So gt here is gt minus 1 plus square of gradient. So what we do is we keep adding the previous value of g, previous value of squared gradient. Okay, we keep adding the square value of gradient to gt. Okay, keep adding it. Okay, and that accumulated value goes to the bottom here. Okay, so that's the difference here in AdaGrad. So what happened is, so that if there is a lot of update in a particular parameter, okay, then that means there are a lot of update means we have this value is very high. There are a lot of update, right? This value should be high. Okay, so that means GT value goes up. GT value is also high. So this value is high means this learning rate becomes smaller, right? This value is high means this is smaller. So learning rate decreases actually. On the other hand, if for a certain parameter, this the update is very sparse, very rare, then this value is very small. Okay, so this in turn that means this GT value is also small. Okay, so this value is small. that means this learning rate is pretty high. Okay, so that means we give high learning rate to those parameters which were less frequently updated. Okay, that's the basic idea of AdaGrad. The second method in learning rate is RMSProp. This was proposed by Jeffrey Hinton in his lecture. This method is very similar to AdaGrad in the previous slide. If you look at the AdaGrad method, the problems of AdaGrad is, if you look at the formula of AdaGrad, it has G here, and actually G is the accumulation of square of gradient. Okay, so you keep accumulating the square of gradient. Okay, so that means this value of G keeps growing. It grows infinitely. Okay, so later on this G value becomes very, very high. So in that case, G is very, very high, then this learning rate is almost zero. Okay, then nothing happens here. So that is the problem of AdaGrad. So to fix the problem in RMSProp, when you calculate G, now we do not keep accumulating. We use this formula. Basically, this is the exponential moving average between previous value of Z and the new square of gradient. Okay, so by using this, now the value of G is limited. It has a boundary. Okay, it does not grow infinitely. It grows to infinite. So its value is now limited. Actually, its value is limited to the maximum value of this square of gradient. Okay. So since it is now limited, okay, this G value doesn't go infinitely. Okay, so that solved the problem. Okay, so because it is now limited, okay, this whole thing, this whole term does not becomes zero. Okay, so that's the difference between RMSProp and AdaGrad. Okay, and Hinton suggested this one here, gamma, to be set to 0.9. Okay, and he said it's very nice default value for the RMSProp. Also, the learning rate here should be 0.001. That is his suggestion. Okay. The next method is AdaDelta method, and this is very similar to RMSProp. So if you look at this formula here, okay, and in RMSProp, this part was eta, constant learning rate. This was constant. Okay, so if you replace this by eta constant here, then this whole thing is RMSProp. So in AdaDelta, instead of using constant eta here, they replace this eta by this one. Okay, this one replaces learning rate constant. Okay, so what is this then? Okay, this one here is this is very similar to the way we calculate G here. So G here was the exponential moving average between previous value and the square of new gradient. Okay, that was the G value. We use exactly same approach here. So S value is the exponential moving average between previous S value plus the square of this value. Okay. So this part is same as RMSProp. So instead of learning rate constant, learning rate eta, we use this one. Okay, This one is basically moving average between previous S and the square of this one, okay? So that's the only difference, okay? So that is AdaDelta. One of the advantages of AdaDelta is we don't need to define learning rate anymore. In RMSProp or AdaDelta, we need to define learning rate eta, but AdaDelta it's replaced by this one, so we don't have to worry about learning rate. Okay. The next method is called ADAM. ADAM stands for Adaptive Moment Estimation. I put some definitions of moment here in this slide. First moment and second moment, etc. But actually you don't need to know this moment to understand ADAM algorithm. So ADAM method is a combination of RMSProp and momentum method. So if you look at this formula, this is formula for ADAM. So if you look here, this one VT hat is actually this one. And this one is exactly the formula used in RMSProp, okay? It's exponential moving average between previous V and the square of gradient, okay? That's RMSProp. So this one goes to here, okay? And learning rate is here. And this one here used to be a gradient, right? And this is replaced by now this one, okay? And this is, if you look this one carefully, this is nothing but momentum. We have gradient and it is added by previous momentum here. So this is a momentum method. So ADAM is basically a RMSProp plus momentum method. So that's ADAM. And when you use MTVT, we use this estimate, and the reason is, in the beginning, when you use MTVT, in the beginning, it is better to start with high value, not zero, okay? Because these are biased, is biased towards zero, okay? So you'll be better off to start with high values of MTVT. So that's why they divide by this, okay? So this makes this MT very high. This makes this VT very high, okay? So that is ADAM. And the author proposed the beta 1 value here to be 0.9 and the beta 2 to be 0.999, and this epsilon should be very small, like 10 to the power of minus 8. Okay, that's ADAM, and it is known that this ADAM method is the best, okay, shows the best performance than any other method like RMSProp, AdaDelta, AdaGrad, etc. Okay, so it's kind of default optimization method for deep learning applications. Okay, next topic is about weight initialization. Okay, so deep learning has a lot of weights, okay, and how do you initialize these values? That is the questions. So the first rule is you do not initialize all weights to 0, okay? If you do that, and especially when you use sigmoid and do this, pretty much nothing is done, okay? Training is not done. So instead, you may initialize the weight using Gaussian distribution with mean equals 0, standard deviation is 1. Okay, that's pretty common practice when you initialize the weight values in deep learning. And actually, we have more advanced initialization method. The first one is called LeCun initialization. LeCun is the person who invented CNN neural net. Okay, so here n in means the number of input node, and n out is number of output node. So the method is simple. When you initialize with LeCun normal initialization, so the value is from normal distribution with mean 0, variance is this, okay? So variance is 1 over n in, number of input node of that particular weight, okay? Or you can choose LeCun uniform initialization. In this case, the W is chosen from uniform distribution between this and this. Again, this is minus square root 1 over NIN, and this is plus square root 1 over NIN. The second initialization method is called Xavier initialization. So for Xavier normal initialization, we select weight from normal distribution with mean 0 mean, and the variance is like this. Okay, so a square root of 2 divided by n in plus n out. Or you can use Xavier uniform initialization. So its minimum is this, maximum is this. Okay, you choose weight from uniform distribution between this and this. The third one is HE initialization. Okay, and it also has normal initialization and uniform initialization. So again, it's quite similar. The weight is chosen from Gaussian distribution with 0 mean, and variance is given as this. And in uniform initialization, you choose weight from uniform distribution from this and this, between this and this. Okay. So Xavier, you can choose any of this, but rule is actually Xavier is quite popular. Okay, so many people use Xavier initialization. So Xavier is effective, especially when using sigmoid and hypotangent. Also, you use Xavier when you use ReLU as well. But sometimes HE is known to be very effective when you use in ReLU function. Okay, these are some other tips you can use in training deep learning. The first one is shuffle. So when you train network, it is better to shuffle entire data. Okay, so that's the first tip of training neural net. The second thing is curriculum learning. Actually, curriculum learning is opposite of shuffle. Okay, in curriculum learning, instead of shuffling entire data, the idea is in the beginning, you provide the algorithm with simple, easy problems, easy data first, okay? And gradually, you provide algorithm with more difficult problems, difficult data, okay? So you start training with easy data, and you gradually use difficult data. So that's the basic idea of curriculum learning, okay? And actually this method, curriculum learning, is known to be very effective when you learn very complex problems. So this one is very effective method. When you try to attack very complex problems, it actually is a good idea to use curriculum learning instead of shuffling, okay? Finally, the batch normalization is, the idea is, so suppose you use mini batch method. So you select a mini batch, okay, and read the batch and calculate gradient and update parameters, okay, and then in batch normalization, you normalize entire parameters, okay. So when the gradient update is done, you normalize them, okay, and start again. That's the basic idea of batch normalization, okay. So this actually kind of solves some problems of vanishing gradient problems, Okay, so this is known to be very effective when training deep learning as well.